Okay, so today we'll be approaching a question that is both approachable through kinematics and electric fields. The question states that a new simulation was incorporated into the Science Center consisting of two parallel plate capacitors. The goal of the simulation was to launch an electron-like golf ball with a total charge of 102 nanocoulombs from the positive plate capacitor to the furthest distance without hitting the ceiling, which is the negative plate capacitor. Hitting the ceiling is an automatic disqualification. So Tiger Woods shoots a golf ball at an angle of 30 degrees with a velocity of 17.0 meters per second, landing 255 meters away. So if the height between the capacitors is 25 meters and the high score is 210 meters away, did Tiger Woods beat the high score? So I will begin this problem by drawing out a diagram. So we know that the bottom is the positive plate capacitor, and we know that the top is the negative plate capacitor, right? We also know that the golf ball, electron-like golf ball, initially starts at rest, travels upwards, supposedly doesn't touch it, travels downwards, right? The distance it travels about 255 meters. Travels with a velocity of 17.0 meters per second, and that electric field is traveling upwards. It's traveling upwards. It's going from positive to negative. And we will also make it such that this is positive and this negative, just so that it's the most logical way to do it, so we don't work with much negative numbers. So listing out our givens, that our delta x is equal to 255 meters, which is our horizontal distance. Our theta is 30 degrees, and our velocity is 17.0 meters per second. And since velocity is a vector, treat it such that 17.0 meters per second. If we want to collapse it in the horizontal way, x is equal to VO cos 30. In this way, in the y direction, it's equal to VO sine 30. So how am I going to approach this question? Is I'm going to first solve for time. And I know that since time is equal in the horizontal and vertical, in the vertical and horizontal, I can use this to solve for our acceleration in the y direction. And then once we have our acceleration and time, we can use these two values and plug it into our distance to solve our distance between the two capacitors. So with this, our V is equal to delta x over delta t. Then if we isolate for delta t is equal to 255 meters over 17.0 meters per second cos 30, since it's in the horizontal, equal to 17.3 seconds. And since we're only solving for one direction, which is going up, our delta t up is actually 17.3 seconds divided by 2, which is approximately 8.65 seconds. So with this time, we can now solve for the acceleration in the y direction. We know that the final velocity is 0, and we know that the initial velocity is 17.0 sine 30 in the y direction over a time of 8.65 seconds, right? And we also know that this is going to equal to 0.983 meters per second squared. And now once we have this and we have this, we can plug it in to our delta distance equation with respect to y, to VOY delta t plus acceleration y delta t squared over 2. Once we plug that in, we would get 17.0 meters per second sine 30 times 65 seconds plus negative 0.983 meters per second squared times time seconds squared all over 2. And if we plug this into our calculator, we would get a value of 36.7 meters. And therefore, since 36.7 meters is greater than 25.0 meters, Tiger Woods' score would not count. And this would make sense because he would therefore have to hit the ceiling, since he hit it with a distance that would result to that. And the second approach to this problem is through electric fields and energy conservation. So it's important to note that since our Q value in this case of the ball is equal to 102 nanometers, right? Which is the same as 0.02 times 10 to the power of negative 7 coulombs. Nanocoulombs, I meant coulombs, right? It's important to note that I just made up this question, so that would mean that this is highly likely not the charge of the actual ball that was used to travel a distance of 255, which could lead to variance between the approach of the electric field and energy conservation method and kinematics method. Okay, so how I'm going to approach this is we know that the Q of the ball, and we know that the Q of an electron, which is a constant. Once we do this, we're going to get the number of electrons, because the units would cancel each other out. And then we will multiply this to mass of 1 electron, and then we will get the mass of a golf ball. All right, and then with this, we will plug this all into the energy, the electric field equation, Y over Q. We would isolate for mass. Mass is equal to E Q over A Y. And then once we have that, we will use our conservation equation, QV initial plus MV squared over 2 is equal to QV final plus MV squared over 2 final. We know that our velocity in the final is 0, so we can cancel that out. We also know that our voltage, assume that it's 0 volts. Cancel that. Once we isolate for our voltage, it's equal to 1 over 2 mv squared sine 30 over Q value. And once we have our Q value, we can take this, and then we can just bring it back to its simplest form, simplest equation, delta E, electric field times distance, and then we can isolate for the distance, which is equal to delta V over electric field. And then if this value and this value, if this value, this approach is equal to this approach, then this value should be about the same, which is 36.7 meters. That's only assuming that this is the actual charge of the ball. But as stated earlier, since I was the one that made this question, it's very unlikely that this is actually the charge of the ball that was used to travel a distance of 255 meters. However, if it was a charge of the ball, both methods would be applicable in this case. And yeah, this video was inspired by the term test. Bye-bye.